Hello everybody, my name is Falastine Abusaif. I am a PhD student in the Nuclear Physics Institute here in Jülich Forschungszentrum. And today I will be talking about the development of compact, highly sensitive beam position monitors for storage wing. So here is my outline. I will have a quick motivation and then I will start directly talking about my research topic, which is the Rogowski beam position monitors. Then we will talk about the calibration measurement for these types of devices, some of the results, and finally arriving at the summary and the outlook. Okay, let's start. The current universe that we are living in at the moment is dominated by matter and not antimatter. And this is one of the biggest cosmological questions that has not yet been answered until this moment. If we try to go back in time, about 14 billion years ago, to the moment when the Big Bang occurred, scientists believe that at that moment we have an equal amount of matter and antimatter, but what we see in reality in the current universe is only matter. And this is the puzzle. Why don't we see antimatter, and where did all those antimatter particles go? Okay. Let's now talk about the electric dipole moment. So in the previous slide, I was talking about the asymmetry in our current universe, the huge imbalance between the amount of matter and antimatter. This means, in other words, that we are talking about symmetry violation, a breaking for the symmetry rules in physics. Unfortunately, the existing rules that can justify the violation of symmetry rules are not sufficient, and we are in need for new resources that can violate the symmetry rules in physics. The electric dipole moment is a very good candidate. Why is it a very good candidate? Maybe I briefly say something about the electric dipole moment of subatomic particles. It's an intrinsic property of the particle. It is pointing towards the direction of the spin axis. And what is very important about the EDM, the electric dipole moment, is that it violates both the parity symmetry and the time reversal invariance. So this means, in other words, we are providing the science, the physics, with new resources that can justify the violation of symmetry rules. And that's why the EDM has gained its own interests. And now I would like to say something about the JEDI investigations. JEDI stands for Jülich Electric Dipole Moment Investigations. It's a collaboration. I am currently a member of this collaboration, and we are running a precursor experiment for the search of EDM. To do that, we are using the little accelerator, the Cooler synchrotron. As a shortcut, we call it COSY. It's a little accelerator with a circumference of 184 meters. It's located here in the Forschungszentrum Jülich in the Nuclear Physics Institute. And in order to measure or to see whether the electric dipole moment really exists, we use a beam of polarized protons or sometimes deuterons. So we study the interaction between the ring electric field and the spin of the particles. By this, we can have an idea about the strength of the electric dipole moment. We are currently aiming at a precision of 10 to the minus 29 ECM, where ECM is the unit of the electric dipole moment as charge times distance. Since we are talking about a very highly precision experiment, this means that we need to have a very high control for the orbit, and we need to know precisely the beam transverse positions in different locations along the ring. And this is my main research topic area, where I'm currently working on the development of some special kinds of beam position monitors that are based on Rogowski coils. So now that was all a motivation, and just before I start talking about my own topic, now I can dig deeper and talk about my research area. So the special types of beam positions monitors that I am working on at the moment, they are based on Rogowski coils. So let's briefly say what is a Rogowski coil before we talk about the Rogowski as beam position monitor. It's simply a toroidal helical copper winding which is wound around a non-magnetic strip. So imagine this, as you can see in the diagram, a toroidal copper helical winding, and imagine having a current source in the middle. If this current source is changing over time, is alternating, is having a frequency other than DC, then according to Faraday's and Maxwell equations, a time-changing electric current will give rise to the time-changing magnetic field. And also at the same time, a time-changing magnetic field will give rise to a time-changing electric field. After all, we'll end up having a potential difference between the wire terminals. And this is the basic principle behind the operation of Rogowski coil in general, where the induced voltage signal is directly proportional to the number of windings of the helical toroid times the time rate of change of the flux that is hitting the surface of the coil. Or in other words, we can say it's the mutual inductance between primary and secondary coil times the time rate of change of the current itself. And that's why it's usually used as a current transformer, as a device that tells about the current amplitude. So that is the basic principle behind the operation of the Rogowski coil in general. Now let's talk about the Rogowski as a beam position monitor, not as a current monitor. In fact, the only difference between the typical Rogowski coils and our Rogowski coil, which is exploited as a beam position monitor, is the geometry. So we take the complete helical winding and we cut it into 4 equal but electrically disconnected wires. By this, as you can see here on the left side of the slide, it's the typical Rogowski coil, and next to it is a winding. This is a picture that was taken for a real winding of the Rogowski beam position monitor. I would like to show you how the device would look like at the end. So at the right side of the slide, you can see the picture for a completely assembled Rogowski beam position monitor. What is very important about this device is its compactness. This is very good advantage for it. It has a profile of less than 10 centimeters. And this is important, especially if you lack the space in the accelerator environment. Then you don't need to worry about having enough spaces or large spaces to install such device. It's only less than 10 centimeters that you need or that is required for installation. Now let's talk about the theoretical background behind the operation of such a device. Remember, I started talking about a voltage signal. So after all, what we measure is a voltage signal. But the purpose of this device is to be used as a beam position monitor. So we need to know the transverse coordinates of the beam. So we need to have a direct link between the measured voltage and the transverse coordinates of the beam. And they are covered through this mathematical formula. It's quite lengthy. You can describe it as a higher order polynomial. In fact, we have higher than the third order, where I stopped in the formula shown in here. And also, we must be having the terms that describe the interaction between the individual windings in the device. Okay, so this is how it is basically related to. You can think about it as a higher order polynomial expansion. Now let's talk about the calibration measurement. So once we build the device, of course, there are so many other steps that goes behind the scenes, but 15 minutes talk is not enough to talk about all these details. So let's say that we build the device and now it's assembled and complete. We cannot directly take it from the lab or from the place where it was constructed directly to the environment where we need to operate it in, like the accelerator, for example. The reason is that it's common sense. You need to make sure that your device is operating as it should be before you go ahead and start operating it as a final device. And for this reason, we have created our own laboratory test stand. So here in this schematic, you can see a schematic for the test stand that we have in our own laboratory. This is the final picture of the device. This is how it should look like, the Rogowski beam position monitor. And remember again, I am saying that we are trying to mimic the accelerator environment by exploiting it in our own laboratory environment. So we need to have a beam source. And in order to mimic a beam source, we simply use a copper tin-coated wire. So this line that is going along the longitudinal axis is used usually to mimic the beam source. So we apply an alternating AC source with a frequency that is equal to the revolution frequency of a beam in COSY. I would like to remind you again, this device is used to deliver the beam transverse positions. So we are talking about positions. So what is missing now is the distance. We need to introduce a distance in the lab. And in order for that to happen, we use the stepping drives. These are the two stepping drives that are in color black. One is having the ability to move along the horizontal axis, and the other one is having the ability to move along the vertical axis. And this is how we usually introduce the motion in our lab in order to calibrate the device. I would like now to say a bit more about the calibration from the point of view of the scanned positions. So we need to scan around the beam line in a way that we get a final picture about how should our device respond and what should the voltage level be at different positions in the two-dimensional map. Usually I use 2 centimeter by 2 centimeter in both horizontal and vertical planes. And if I start, let's say, plus minus 10 millimeter with individual steps of 1 millimeter, that means the over number of scanned grids is 441. For each one of these scanned grids, we also measure the voltage response from the 4 individual quadrants. And by this, we end up having a complete picture about how should our system react and what should the signal level be at different scanned positions. And now we can talk about the achieved resolution by this device. The resolution as a word, it means the smallest detectable or measurable, let's say, range in distances. But in our case, it also means the same thing, but how we do it, we simply have 2 different maps. The first map is the measured map in positions that we do in the laboratory, and the second map is that reconstructed using the theoretical model. And what we do, we make a suppression between individual grids that are corresponding to each other, between the theory and the measurement. So in other words, we look for the difference between the measurement and the theoretical expectation. And this is how the result look like. So in the both axes, the 2 little subplots are showing the resolutions, or let's say the difference between the measurement and the theory. On the vertical axis is the difference in the y coordinate, and on the horizontal axis is the difference between measurement and theory in the x coordinate. The main axis represents a 2-dimensional histogram for the main data plotted in the graph. We could reach a resolution in the horizontal axis of 142 nanometer. We also could reach in the vertical axis 104 nanometer. And the agreement, in fact, between theory and measurement was very good. Okay, let's talk about a coil that was installed in the accelerator environment. So this device was installed in COSY, and here is a schematic for COSY ring with a red cross showing where exactly the Rogowski beam position monitor was installed. Here is a real photograph that was taken for the device, and it was installed next to the RF beam filter device, which is to the right side, and you can see also the quadruple to the left side of the beam position monitor. Once we installed the device in the accelerator environment, we also wanted to make sure that the system is operating the way it should. For that, we have applied an orbit change. So we exploited a change in the orbit locally next to the device at the location where the device was installed. And this change that we introduced to the orbit was applied in the horizontal and in the vertical plane. So what you can see here in this on the left side is the applied orbit settings that were performed in both directions, in horizontal and vertical plane. And what you can see on the right side of the graph are the measured positions as delivered by our system, our Rogowski beam position monitor. So we were looking for a linear response and reproducible measurement, and this is what we got. So the system was acting linearly, meaning the more the settings that we were applied, the more the change that we introduced to the orbit, the more the distance we measured. Similarly, if we were scanning the same, or if we were not introducing any change, let's say, to the orbit, that means we are measuring the same exact point. Any point of these 3 points corresponds to 3 repeatable measurements. So what we got, after all, a reproducible and a linear response, which should be the case. This brings me to my summary and outlook. New types of compact, non-destructive beam position monitors have been developed recently. The resolution down to the 100 nanometer region has been achieved. One Rogowski beam position monitor was successfully installed in the accelerator environment and tested there. Further improvements are needed to optimize the test and operation conditions. At the end, I would like to thank the Palestinian-German Science Bridge for giving me the opportunity to do my research topic in the Forschungszentrum Jülich in this field in particular. Thank you very much.